Hello, everyone, and welcome to our first topic. And our first topic is evolution. Now, evolution is something that really fascinates me, and I'm hoping it's going to interest you guys as well. There's a very famous saying in biology that nothing in biology makes sense except in the light of evolution. And this is a quote from a rather famous population geneticist, and we'll talk about population genetics later in the course. But what this researcher was suggesting is that in biology, in living things, there are some weird structures, some weird behaviors, things that don't seem to make sense. We have some structures that maybe don't have much of a purpose. We have some metabolic pathways that are really inefficient. We have some redundancies and so on. Why would that exist? Well, it does make sense if we consider the fact that organisms change over time. Structures that were once useful might stop being useful. Structures that were used for one particular task might be adapted for a new task. So we have in our bodies kind of a history of what happened before. Now what you're seeing here is a photograph that I took actually of a ball python embryo. So python is a type of snake, and in pythons and also in boas, there's these weird little nubs at the back of the embryo. So the front of the embryo there, that's where that big black thing is, that's the developing eye, and then down the other end towards the tail, we have these two little buds, and these are limb buds. So as vertebrates develop, as you developed, at one point you had little buds that became your arms and little buds that became your legs. And you're seeing those hind leg buds here. Now, of course, the adult snake doesn't have legs. It does have some little tiny spurs down there, and we'll talk about that in a moment, but of course there are no legs. But snakes evolved from animals that did have legs. And these little buds do actually develop into a very tiny leg-like structure that contains a few bones. It contains a femur and a tibia and a few other bones. So it makes sense that these things would be there if snakes evolved from reptiles with legs. Otherwise, it doesn't make a lot of sense that those buds would be there. And it's thought that snakes evolved from mosasaurs, which were marine reptiles that lived in the age of the dinosaurs. I'd like to start by taking a bit of a look at the history of biology and the history of evolutionary thought. In the beginning, people weren't thinking that animals and plants evolved and changed over time. Most religions, which is how most people formed their beliefs, suggested that living things were created all at once. God had a plan. They were created the way he or she wanted them created, and they did not change over time. What you're seeing here is the depiction of the creation of Adam, the first man, by the Christian God. Humans try to make sense of the world around them. And one way we can make things work better for us and more manageable for us is to put organisms and other things into categories. We'll talk later about how we define different groups of animals and plants. We'll spend a lot of time doing that. If we go back to ancient Greece, back to Aristotle, he thought that he could fit everything into this hierarchy that he called the great chain of being. Now, unfortunately, this also suggests that, some organisms are better than others. They fit onto this ladder, this ranking system, which is not quite the way biologists think nowadays. But early biologists did follow something very similar to this great chain of being. So what is that? Well, Aristotle said that you had some things that just simply existed. That'd be things like rocks, minerals. There were some things above this, and he would suggest that they were perhaps better, that not only existed, but there was some sort of life force to them. Here we're talking about things like plants and fungi. Above that, we had things that were a bit better. They existed, they had life, but they also had motion. So now we're talking about animals. Animated means capable of motion. And these things also had an appetite for food, but also an appetite for sex, a lust. Above that, we had humans. And humans, of course, existed. They had life, they had motion, they had appetite, but they also had spirit. They had a connection to the gods, the Greek gods. And then above that, we had entities that were just spirit. These were the Greek gods. This system of ranking organisms continued well into the 1800s. It existed for centuries. And here we're seeing an etching from 1579, and you can see that everything has been ranked. Down the bottom, we have rocks and minerals. We have the crust of the earth. We have plants. Above that, we have animals and then birds. And then you can see people are on two tiers there. So we have our lowly peasants, and then at the top we would have kings and queens and so on that were closer to God. They could communicate directly with God. They were picked by God for their roles as kings and queens. Above that we have angels, and then we have God at the top. Some people took this ranking even further, and I've put that on the side here. It's interesting where they would put things like actors. You can see actors are way down there between beggars and thieves and pirates. But this is kind of the ranking system that people would use for humans, unfortunately, but also for living things. And this way of thinking carried through biology for much of its early development. And I should point out that this is not a history course, so I'm not expecting you to memorize dates or anything like that. I just thought I'd give you a little background. I also want to point out that although it might sound like it, I'm not trying to diss religion in any way. In my mind, religion is something you really can't test. It's outside of the scientific method. It's very, very difficult to test the existence or non-existence of a God. So I hope no one gets the impression that I am attacking their beliefs. The one thing I will refute, though, is the age of the earth. So if we take, for instance, the Bible literally, the earth's not very old. And also, if we take the Bible literally, everything was created as we see it today. Animals and other organisms don't change over time. Now, we can use evidence to refute the age of the earth and also the fact that organisms don't change. So here we've got a painting of what it's thought the Garden of Eden might have looked like. And a quote here from Genesis, from the Bible. "And God created great whales and every living thing that moveth, which the waters brought forth abundantly after their kind, and every winged fowl after his kind. And God saw that it was good." So the idea here is that things were created exactly as we see them today, and all the animals that were found in the Garden of Eden have not changed since then, although some may have disappeared. Some scholars at the time took Genesis very, very literally. Famously, James Ussher tried to figure out how old the earth was based on Genesis from the Bible. What he did was he looked at the family trees represented in the Bible. Of course, the Bible goes into great detail about so-and-so begat so-and-so, etc. And working from that, he gave us a date for the Earth. He said the Earth started in 4004 BC on October 22nd at dusk. That's very specific. Now again, there is very good evidence that the Earth is much older than that. Well into the 1800s, most biologists were doing what we would call today natural theology. They were looking at the world around them, making observations, and then deciphering all of that information with respect to their religious text, whatever that might be. So in the case of Carolus Linnaeus, it was the Bible. He would go out there, he would classify organisms, try to make sense of everything, and put names to God's creation. You've probably heard of this guy before. He did quite a good job of classifying things. Now, he didn't think that things were evolving or changing. He believed that everything was created all at once in the Garden of Eden, and things had not changed. But he looked for characteristics that he could use to put different organisms together. And he picked really good ones that we still use in many cases. So for instance, before Linnaeus, people classified fish and whales in the same group. In fact, whales were quite often referred to as fish. There's a reference to whales as fish in the Bible, for instance. But he recognized that whales were different than fish. They had a blowhole, they breathed air, and they also produced milk. So breathing air, producing milk, those are characteristics that we associate with mammals, and he classified them as mammals. He also gave us the system that we use to name all living things. It's called the binomial system, bi meaning two, nomial meaning name. So all living things have a proper scientific name that's in Latin and consists of two parts. For instance, Homo sapiens. That would be the correct Latin name for humans. A lot of the groups he came up with, we still use today. Aves are birds, amphibia, that would be frogs and toads and salamanders, etc. Pisces, fish, insecta, the insects. Some of the other groups we don't use, vermes, for instance, those are worms. We have a better classification system for all the invertebrates now. Paradoxa, these are things that were a paradox. He didn't quite know where to put them. But he made a massive effort to classify things. He didn't think things were changing, so he didn't classify them in terms of evolutionary relationships, of course, like we do today, but he did a pretty good job, and we'll come back and look at this when we talk about taxonomy, which is how we classify organisms. Alrighty, let's take a look at one of our earliest theories of evolution. Evolution, again, relates to changes. Organisms changing over time. This fellow here was a French biologist by the name of Buffon. He was doing his work in the 1700s, and he came up with a theory that organisms could change, and that was pretty radical at the time, and he was very, very careful about how he worded it. At the time, the word evolution was not used the way it is today. Evolution back then referred to embryonic development. Instead, if people were talking about how organisms might change over time, that was called transmutation. So he had a theory of transmutation, and it was an interesting one. He thought that species could degenerate over time. So again, remember, all biologists are kind of thinking about life as a hierarchy, and some organisms are better. They're inherently better somehow than other organisms. He thought it would be blasphemous to say that species got better, because that would mean God didn't make them right. So he imagined that there was a moment of creation. God created everything, but God made everything perfect. Things could not get better, but they could degenerate. So for instance, He had access to lots of fossils, particularly fossils of extinct forms of elephants. So we only have 2 species of elephants at the moment, but in the past, in the distant past, we had about 18 species, and he had knowledge of some of those. So he had seen fossils of mammoths, and he thought mammoths were pretty cool. You know, they're massive, they've got big tusks, and he thought that the mammoth was the perfect elephant that God created. This is the elephant that was in the Garden of Eden. Now, when the elephants started to migrate out of the Garden of Eden, some of them degenerated. They lost those big tusks. They got smaller. They got kind of wimpier, I guess, giving us the elephants that we have today. But the important thing to note is that he thought things could degenerate. They couldn't get better. They couldn't get better than how God made them and put them in the Garden of Eden. He also coined the term vestigial organs, which is a term we still use. This is the idea that there can be structures in an organism that aren't particularly useful, but they were useful before. So if we have, let's say, an organism that degenerates over time, we might be left with these vestigial organs that have degenerated themselves and they're not that helpful anymore. Look at this cute little guy. Now this is a mole, and this guy would be burrowing underground. There's something missing. He doesn't have any eyes. He's actually got tiny little vestiges of eyes. So there is still a little kind of dimple, a little divot in the skull. Some moles will have very tiny eyes. They tend not to work particularly well, but this guy here you can see, yeah, there's no eyes. Buffon, seeing something like this, would suggest that the original mole that God created was perfect and it had eyes, but the eyes degenerated in this particular species. And they degenerated because they didn't need them if they were burrowing underground. In fact, if you're burrowing underground and you've got great big eyes, they're going to fill up with dirt. They're not going to help you because you're in the dark. So having eyes is actually not helpful. They're just going to get infected. And this particular species degenerated and lost those eyes. Here's another example of an organism that has quote unquote degenerated. These are cave fish. So they live in caves in fresh water, deep underground, and they've lost their eyes, as you can see. They actually, when they develop as embryos, they start developing eyes, and then the eyes abort. They also have no pigment because there's no need for pigment. They live their entire life in total darkness. There's no need for pigment for camouflage. There's no need for pigment to attract mates because your mates can't see it, so they don't bother making the pigment. Now this makes sense. Why would you make eyes? Why would you put all that effort and energy into building eyes if you don't need them? Why would you make pigments if you don't need pigments? But again, it's a case where we started out with a so-called perfect organism and it has degenerated. It's lost these sensory structures. A couple more examples. One you've probably heard of before, the appendix. Where your small intestine meets your large intestine, there's a little swelling called the cecum, and then hanging off of that is the appendix. And the cecum and the appendix are very small in humans. In a lot of other animals, they're huge. In animals that eat a lot of cellulose, which is really tough to break down, they have a large cecum and a large appendix. It would seem that the appendix in us doesn't do very much. It's thought it doesn't do absolutely nothing. In fact, there's some bacteria in there that might be helpful, but it certainly doesn't do as much as it does in many other animals. And it may be that our ancestors had a more developed appendix and we lost it over time. In the other photo there, the large photo, you're seeing the anal spurs I mentioned before. So this is an adult python, and those little buds develop into these little spurs. They're not entirely useless. They are used by males to grab onto the female during mating, but they of course don't function as legs anymore. They're degenerated legs. So we refer to these structures that don't have much of a function anymore, but presumably did in the long distant path, as vestigial organs. They're a vestige of what they once were. Let's take another look at an example of the degeneration of limbs in animals. It's actually pretty common. In Australia, there's a group of lizards that all belong to the genus Lyrista. There's about 40 different lizards. They're all quite small. And they all differ quite a bit in what they have in the way of legs. This one here, you can see it's got fully formed front and hind limbs. This one here has become stretched out and it's very snake-like, and the limbs are very tiny and probably not that useful. And then this one here looks almost exactly like a snake, although if you look carefully, there are some tiny, tiny forelimbs. Now, why would these lizards lose their legs? Well, getting around like a snake is actually quite helpful. If you're going through debris, if you're going through leaves and rocks and bits of wood and so on the surface of the ground, you can get through that material quite a bit quicker if you don't have legs. In fact, the legs kind of get in the way. So they can burrow into this debris like a worm would. And if you look at their forelimbs, so here we're looking at their front limbs, we can see that some of them have fully formed toes, and some of them, the one on the far right there, we've just got one toe, and the same with the hind limb. So across these 40 species, we see a huge variation in what their limbs look like. So again, if Buffon had seen this, he would say, okay, well, the original lizard that was made by God, it was perfect, but some of them lost their limbs because it was helpful. And of course, today, this is what we think of when we think of evolution. Evolution doesn't always make an organism more complicated. In some cases, it makes it simpler. It just makes the organism better adapted to its environment. Now, you'll have to excuse me if I'm showing too many pictures of lizards and snakes and so on, but my PhD work was in snake evolution. I do find snakes quite fascinating. This here is not actually a snake, though. It's a lizard. It looks like a snake, but if you look closely at the front end, and that's towards the right, you can see two little limbs. And they're not entirely useless. This guy looks pretty cute. He's got these two limbs there with some pretty wide fingers or toes that it can dig with. So it'll dig with those front paws. It's got no back legs whatsoever, and then it can burrow through the soil like a worm. And in fact, if you come across one, it does look a lot like a worm until you see those weird little legs on the front. They're really kind of terrifying up close. So Buffon gave us one of our earliest well-documented theories of evolution. He very bravely suggested that organisms can change over time. But remember, he only thought that structures could be lost. He didn't think that new structures could be gained, because if he believed that, then he would be suggesting that God missed something. God didn't add something that the organism needed. But he did suggest that when organisms lost structures, the reason that occurred was to make them better adapted to their environment. So for instance, the mammoths that were created in the Garden of Eden, when they migrated out into much warmer climates, they didn't need that big fur coat and they lost it. Unfortunately, Buffon kind of backpedaled in his later years. I think he was a bit frightened of how the religious community would receive his theory. His theory really never got out of France until much, much later. Okay, so let's move on to something a bit different. So at this point in time, in this little historical journey we're going on, some biologists have started suggesting that life changes over time. And they're realizing that these changes probably occur pretty slowly, and so it would require a lot of time. More time than is suggested by the Bible and most other religious books. Geologists were coming to the conclusion that the Earth was actually much older than is stated in the Bible and other books. And let's talk about how they figured that out. So I'm going to start with a very, very simple idea here. It's something called the law of superposition. Now imagine that we have a river that's emptying into a lake, or it's emptying into the ocean. The river is going to carry silt and sand and other sediment, and that's going to collect on the bottom of the lake or the bottom of the ocean. It's going to collect in layers. The layers at the bottom are older than the layers at the top. So we can see here this lake, for instance, has filled up with sediment, completely filled up, and then later on a river has cut through it, and we can see all the sediment layers that were laid down. The ones at the bottom are older, the ones at the top are younger. So younger layers or strata are laid down on top of older layers. And when geologists started looking at these layers, they found fossils. And they noticed that the fossils changed from layer to layer. If we go to the Grand Canyon, we can see layers of sedimentary rock. So sedimentary rock is rock that was made from clay and sand and so on that got squished under a lot of weight, a lot of pressure, and turned to stone. So we can see these layers in the wall of the Grand Canyon here, and we know that the layers at the bottom were laid down first, and therefore they're younger. So if you go to the Grand Canyon and you walk a trail from the top down to the bottom, as you go deeper and deeper into the canyon, you're encountering older and older rocks. Now there's another question here though. This is a big canyon. How did this canyon form? Let's talk about that a bit. There were two different theories as to how something as big as the Grand Canyon could be created. One theory is called catastrophism. And the name suggests that there's a catastrophe involved. So here's a guy, George Cuvier, and he was a believer in catastrophism. So if he had seen the Grand Canyon, he would have said, aha, there was a great flood in the past with so much water that it cut out the Grand Canyon. And maybe that only took a few weeks. So maybe that was the receding floodwaters from the Great Flood of the Bible, for instance. So if you believe in catastrophism, you believe that structures like mountains, deep valleys like the Grand Canyon are created over a very short period of time. But in the 1700s and 1800s, there was also a group of geologists that believed in something called uniformitarianism. And uniformitarianism suggests that things happen very slowly. So this guy here, James Hutton, a very famous Scottish geologist, he was apparently standing by a riverbank once, and he was watching the water, and as he was watching the water, a little chunk of the bank fell off into the water and got carried away. And he had a eureka moment. He thought to himself, what if this simple erosion happens for a really, really long time? What if the Grand Canyon is not young, but it's very, very old, and it was actually carved by that river at the bottom over a very long period of time? So just very slow, constant, gradual erosion could create a very, very big canyon if given enough time. Now that, of course, would mean that the Earth would have to be quite old for there to be enough time for something like the Grand Canyon to be created gradually. Now the year that James Hutton died, another guy, another geologist by the name of Charles Lyell came along and kind of took up his way of thinking. And he has a rather well-known quote, "The present is the key to the past." So what he thought is, if you want to know how things are created geologically, go out and just take a look at what's happening now. So you go out and you study erosion. You go out and you study the deposition of sediments in a lake bed or at the bottom of the ocean. And he saw that these processes could account for all the landforms that we see, but they happen very slowly. So mountain building, it was suggested that, well, we didn't know this until much later, but it was suggested that the land was being pushed up very, very slowly over very long periods of time. So these geologists and other people that believed in this gradualistic model were quite important because their research suggested the Earth was very, very old, and biologists were thinking that evolution might be a thing, but it would take a very long time. Well, now it appears that the Earth might indeed be old enough for things to evolve, because 6,000 years is not enough time. But now we're talking about hundreds of thousands or millions of years. Our next person of interest is Jean-Baptiste Lamarck. He was a French biologist, and he actually worked at the same museum in Paris as Georges Cuvier. Cuvier was his boss, and Cuvier did not like Lamarck. And that's because Cuvier did not believe in evolution. He thought the Earth was very young. He thought that there were catastrophes in the past, like Noah's flood, that carved out canyons and also caused extinctions. So Cuvier, interestingly, introduced us to the idea of extinctions. He saw that there were bones of giant animals that don't exist anymore, and he thought that they were made extinct in massive floods and other catastrophes. But anyway, Lamarck did believe in evolution, and he believed that the Earth was very old. So you can imagine how him and Cuvier didn't get along very well. And Cuvier gave him all the jobs that no one else wanted. So they were working in this museum, they were classifying things and describing things, and Cuvier made him work on insects and worms and all the creepy crawly things that at the time no one was really interested in. That's actually a good thing he did, because Lamarck did a good job classifying those things. But anyway, Lamarck had his own theory of evolution, and we now call it Lamarckian evolution, which is a bit of a misnomer because people that were thinking about evolution at the time, most of them were thinking along similar lines as Lamarck. So what did Lamarck believe? Well, his theory of transmutation, again, that's the old word for evolution, was that organisms changed over time, but they got better. There was this progression towards perfection. So things always got better. He believed in spontaneous generation. That's the idea that the air can breathe life into non-living things. Now that might sound really crazy, but at the time, most biologists believed that. So he believed little organisms, little invertebrates and so on, could spontaneously generate, and then over long periods of time, those organisms would climb up the ladder. They would climb up the chain of being and become better. Now, he also believed in what's called the soft theory of inheritance, or the use and disuse theory. This is the idea that if an organ or a structure gets used a lot, it will be enhanced, and that enhancement will be passed on to the offspring. The classic example of Lamarckian evolution is the development of the giraffe's neck. Lamarck believed that giraffes started out with short necks, and in fact we know today that giraffes evolved from something kind of similar to a zebra, but they started out with short necks. The ones that had longer necks were able to reach branches that their buddies couldn't. So if you had a longer neck, then you could reach food that your competitors could not. But he thought that the giraffes had this drive. There was this inner need, this inner drive in every living thing to get better. And he believed that the giraffes actually stretched their neck. So by reaching so hard over the course of their life to try and get these branches, maybe they physically stretched their neck by an inch. And they passed down that improvement to their children. So when this giraffe had offspring, had babies, they would start out with a slightly longer neck. And then those giraffes would stretch their necks just trying to reach these branches. And this improvement that they developed through really, really wanting to improve and trying hard to improve would be passed down to the next generation. Lamarck also discussed a human example. If you're a blacksmith, you're swinging a heavy metal hammer all day and pounding metal, and you develop a powerful arm. So let's say you're right-handed. Your right arm might be far more muscular than your left. Now, Lamarck noticed that the sons of a blacksmith had this same peculiar trait. Now, if he'd thought about it a bit more, he might have realized that the sons were blacksmiths too, and they actually build up those muscles just like their father did over the course of their life. But if you're a believer in Lamarckian evolution, you would think that building up that arm over the course of your life, that trait that you developed through use, would be passed on to your children. They would start out with bigger arms. So let's say you're a rather scrawny guy and you go to the gym and you work out and you get really big and buff. The idea with Lamarckian evolution is that you would pass that acquired trait, so a trait you acquired during your lifetime, you would pass that on to your children. They would start out with that trait being enhanced. Likewise, if you had a structure in your body that you didn't use, it would wither. And when you had children, that structure would start out smaller. So that might explain vestigial organs. Now, of course, we know that this isn't what happens. We'll talk about what really happens in a moment. Lamarck gets kind of a bad name for believing this. He's kind of laughed at quite often, which I think is really unfortunate because almost all biologists living during Lamarck's period believed in this use and disuse theory where acquired characteristics could be passed on to children. In fact, Darwin, who we'll talk about in a moment, also was unsure about this. Lamarck did a lot of amazing things. He came up with a theory of evolution that had some parts that were right, some parts that were wrong, but understandably so. He did a really good job classifying invertebrates. We'll maybe talk about that a bit later on. Sadly, he died penniless. He actually had to rent a coffin, and after about 10 years or so, they needed the coffin, and they took his bones and threw them in the catacombs of Paris. No one knows where his body is. Whereas Darwin, who gets all the credit for the theory of evolution, ended up buried next to Sir Isaac Newton. And of course, that brings us to the big man himself, Darwin. Now, Darwin didn't come up with his theory of evolution all on his own. He took bits and pieces from lots of other people, lots of other theories. He took a lot of it from Lamarck's theory, in fact. But he picked the good bits from these different theories. He came up with a theory that worked really well at explaining what we see in the natural world. Most importantly, he gave us a mechanism for evolution. And the mechanism is something known as natural selection. And there was much celebration. So I'm going to stop there for now, and because this is a long topic, and we'll continue by looking at Darwin's theory, what it is, how it works, why it works, and how it has withstood a lot of scrutiny and testing.